Okay, we're here to learn about Gauss's law, and you should already be pretty confident in your understanding of electric flux. Otherwise, you're not going to understand this well. So Gauss's law, flux is a concept and we have a definition. Flux equals the integral of E dot dA. Gauss's law, understand the difference. Gauss's law is a relationship between flux and the charge inside. And Gauss's law applies only to closed surfaces. So you see this CS? Gauss's law is something that's applied to closed surfaces. And so what this says, if you calculate the electric flux over a closed surface, could be a cube, could be a sphere, could be any weird shaped thing, as long as it's a three-dimensional closed surface, and we indicate the closed surface in the double integral by this circle. So you'll see this symbol for closed surface and you'll see this. So if you calculate the integral over a closed surface, in every case that flux will be equal to the charge inside divided by epsilon naught. So this is a relationship. Gauss's law is a relationship between flux over a closed surface and the charge inside the surface. It is not a definition of flux. It's a relationship. So remember that. Keep that in mind. Also, recall that epsilon naught is the number inside K. So K is, if you recall, we called it a convenience constant. It saves us from writing 1 over 4 pi epsilon naught, because epsilon naught, it turns out, is the fundamental electrostatic constant of nature. And all this is 10 to the 8.99, if you will, times 10 to the 9 Newton meters per coulomb. Epsilon naught is this number. And notice the units of epsilon naught are exactly the inverse of the units of K. So this is epsilon naught. It's the number that goes here. Now let's look at some examples. So in this video, unless I say otherwise, we're just going to consider two-dimensional space. So we have this point charge with an electric field represented by electric field lines, and now I'm going to create a closed surface. So I'll make a sphere. Well, in this case, 2 dimensions, it's going to be a circle. So there's my closed surface. In 2 dimensions, it's closed. And now I'm going to move it into the field. Wait a minute. No, I don't need that. Well, I can't move it. Let me figure this out. Okay, I'm back. Let's try this again. Here's my closed surface. It's a circle in 2 dimensions, or if we were in 3 dimensions, it would be a sphere. And now let me see if I can move this. No, whoops, screwed up again. Hold on. Try again. A circular or spherical closed surface. It still doesn't work. Okay, finally I got it to work. I have this sphere now that I can move around. And this is a little bit deceiving because these field lines don't stop, right? They just go on and on. So I should have made them a little longer. But let me move the sphere into what we can see as the field. If I put it here, notice that, and remember that electric flux, we know how to calculate it, but we can also think of it as the number of field lines entering or leaving. So if we look at that, we see 2 field lines entering the sphere and 2 field lines leaving the sphere. So even though this would be difficult to calculate because the field is not uniform and the angles are different everywhere over the sphere, we can see in a simple conceptual way that the flux entering the sphere and the flux leaving the sphere are the same, minus 2 and plus 2. And so we get that the charge inside the sphere is 0. So let's move it to a new place. If I move the sphere here, now count. What's the net flux through the sphere? Pause the video and get the net flux through the sphere. All right, you should see 3 field lines going in, 3 field lines coming out. The net flux is 0, and consistent with Gauss's law, the charge inside is 0. Now watch, if I do this, if I place it so the charge is inside, now what is the net flux through the sphere? Pause the video and think. All right, so you see 12 lines leaving the sphere, no lines entering. So the net flux through the sphere in terms of field lines is 12. In terms of Gauss's law, it would be whatever this charge is divided by epsilon naught. So you could put a number in there. You could say, let's just pause and I'll do a number so you can see how it works. So once again, notice that we have 12 lines leaving the sphere, and so there's a net flux out. And we could figure out what the flux out of this is by doing this integral. I'm not going to take that approach, but it could be done. But instead I'm going to use Gauss's law, which says that the flux through the sphere is simply the charge inside divided by epsilon naught. We know what the charge inside is. I'm going to make 1 nanocoulomb per line. So the charge inside, I'm calling it 12 nanocoulombs, 12 times 10 to the minus 9 coulombs. And so I simply use the Gauss law relationship, and I say the flux through the sphere is going to be that charge divided by epsilon naught, and I get this, 1.36 times 10 to the third Newton meters squared per coulomb. I realize now that in the last video I didn't talk about the units of flux. So just notice now, E is newtons per coulomb, A is going to be meters squared. So that's the units of flux, and it doesn't have a name. We just write it out, Newton meters squared per coulomb. Now notice, if I take this sphere, like right now if I center it, we could, if you're in Calc 2, you might realize that this integral would not be difficult to do. And yes, if we did this integral, we would get this same result. Of course, it's much easier just to do this. But supposing I did this, supposing I move the sphere so it's like this. Now, the field strength over the sphere varies, and the angle varies, and so the integral would be difficult to do. But the flux, Gauss's law tells us that the flux is simply this. Okay, let's pause and look at another example. Okay, so you see I reduced the former screen and put it off in the corner, and I drew what you should know. What's it called? Yes, an electric dipole. And notice the number of lines leaving the positive charge are equal to the number of lines entering the negative charge, and I chose a scale of 12 to 1, so we'll consider this charge a positive 12 nanocoulombs and this a negative 12 nanocoulombs. And now I want to calculate the flux through some surface. So in this case, I'm going to create a box. So I'm going to make a square, and we can think of it as 2-dimension square or a 3-dimensional cube. Okay, here's my dipole that I showed you with 12 lines, and here's my, here's my Gaussian surface, my imaginary cube or square. It's not actually square, but anyway. So if I put the square here and we get the flux from counting lines, you can see that 1, 2, 3, 4 lines enter, 1, 2, 3, 4 lines leave. The net flux through the rectangle is 0. The charge inside is 0. It agrees with Gauss's law. If I now slide the square here, I have 12 lines entering and 0 lines leaving, so the net flux is a negative 12. That's what's inside there, a negative 12 nanocoulombs. If I place the rectangle here, I have 12 lines leaving. If I were to place it here, I would have, say, 8 lines leaving because I have about a little less than half the charge inside, so half the flux leaving. And so no matter where I put it, the result I get is consistent with Gauss's law. If I put it right here, then there are 12 lines leaving and 12 lines entering, and the net charge inside is 0. So notice that Gauss's law does not say that there's no charge inside. It says up here in the small font, it says that the net charge inside is equal to the flux, and so the net charge inside is 0. There's 2 charges inside, they cancel, the net charge is 0, the net flux is 0. So in some of the lab problems, you'll have a dipole and you'll have a uniform electric field and you'll have a single charge field. And notice that if we were to try and calculate this integral, it would be next to impossible because the field lines entering the surface are of different strengths in every place and different directions relative to the surface, and so we would have to do an integral by dividing every bit of this surface into little dAs and doing an integral. Clearly a difficult to do integral, but by using Gauss's law it becomes very easy to get the net flux out of the sphere. Out of the cube. Okay, I think we're done.